So in the second problem, basically he said he is welding, okay, and so out of that spark he's making basically droplets end up basically flying by, ejected from this, and so he consider a molten droplet. So this is basically a droplet that's very hot, and it's leaving that weld, and it's moving at 1 meter per second. Does that velocity mean anything to us? Does it make any difference whether it's moving faster or slower? Huh? Can't hear. Yeah, why? Why would it make difference? Convection. It may cool faster if it's flying faster. That's called natural convection or forced convection? Forced convection. So that's why we have this velocity. Right? On top of that, because it's really hot, he said its initial temperature, T initial, is 1700 Kelvin. So as the temperature gets so hot, we know that radiation become really important. You know, when you are at like 300 degree Kelvin, radiation is not as important as when you are 1000 or 1700 Kelvin. Then radiation become, because it's T to the power 4, right? So huge difference. So that is the initial temperature of this droplet, and that's its velocity. And he gave us the diameter. So the diameter is 0.5 millimeter, right? And he said the air, T air over here, let's call it T air, is 300 Kelvin, and required the rate, initial rate of cooling, dT by dt. Because it's super hot and it will radiate like crazy, and because it's also have convection around it, it will cool down. And he would like to know what is that rate. You're basically trying to figure out how long before the thing will basically become solid, right? So, you know, in the old time when they were trying to figure out the fuel injection in jet engine airplane, and they didn't have the laser technology to basically measure droplets flying, they used to inject wax. So rather than the fuel, they would inject molten wax. And so the wax would come as liquid, break from the fuel injection as droplets, and those droplets, by the time they hit the floor or the bucket they are collecting on, they are a bunch of spheres. And then they collect the spheres, and basically they, using sieves or something, they distribute them into, well, here is how many large and how many small, and they get the whole distribution out of those droplets, right? So it's similar to something like this. So if you don't cool enough or don't cool quickly enough, those droplets may fall down in the bucket as still molten droplets, and then you will be collecting a disk of wax rather than individual droplets, right? So how should I think about getting this rate of cooling? What equation will give me this? Which equation would have the rate of temperature decrease or increase? It's decreasing this time. What equation will offer this to us? Huh? Someone asked you, this classroom, we started with 70 degrees Fahrenheit, and then all the students came in, and we are wondering, you know, how hot it will get and how quickly it will get, so that they will basically start complaining that it's really too hot for them. You know, for example, you know, all the malls and stuff, the commercial mall, the temperature is actually in the summer, it's not really comfortable, it's really hot. But because you are coming from a hot air outside, when you come in, you feel, wow, it's so cool, and hopefully you will finish your shopping and get out before you realize it's not really comfortable. But the people who are there, they know that, no, it's actually too hot, but we are saving energy on it. So in both example, you know, how do you calculate the temperature of you coming into that building and getting the temperature adjusted, or what equation control that? Anyone? Huh? I can't hear. Looking. It's in thermo. And it's the first thing that you guys learned in thermo. It is first law of thermodynamics. Right? The first law of thermodynamics for a system basically can tell you how much is the rate of change of the internal energy inside that system. Well, the internal energy is mCV_T, right? The first law basically say Q dot minus W dot is du by dt, really, kind of, right? And I mean, this droplet is not gonna do any work. So it's basically Q dot is du by dt. If you give me heat, I will increase my internal energy. If you suck heat out of me, I will lower my internal energy, my mCV dt, right? So there is actually not just one Q, there is two Q. Okay, so let's, so this will translate into basically, so that Q, because it's cooling, the Q will be minus. Okay, so minus Q dot radiation, minus Q dot convection, and then in this Q convection I will put a plus number, but I'm saying it's minus because it's leaving my system. Okay, I'm sending heat out, and this will be equal to mass time CV time so this would be in watt, this would be in watt, and now this is also in watt. Right? If I'm losing, if this guy is making me lose 1000 watt per second and this guy is making me lose 200 watt per second, then the internal energy of this guy is basically gonna drop 1200 watt, 1200 joule per second. We're gonna lose, and that will show up not as a loss of mass or a loss of CV, it will be a loss of temperature. The temperature, the indicator of how large the energy is, that dial will just get lower and lower and lower. So that's really the, if I'm grading the final on a problem like this, I would say this problem, this is 50%. Just getting the cornerstone of the problem. Okay, now, so let's fill in the blank. I need my M, I need my CV, I need my Q convection, I need my Q radiation. So in the problem, he actually gave us the specific heat, right? He said liquid aluminum property at 1700 K, that's the initial temperature, and he wants that thing initially at T equals 0. As time go by and the temperature drop, his Q radiation will drop and his Q convection. We have the CV, it's how much? 1100. That's the CV, all right? And we have the M, not really, but he gave us the rho. So the M is rho multiplied by the volume, and the volume is, for a droplet, pi over 6 d cube. It's also 4 over 3 by r cube, right? Same thing. So 4 over 3 r cube is the same as pi over 6 d cube. So now we have the volume, okay, and we have the CV. So all we need is Q convection and Q radiation. So in the hint, he also gave us the Q radiation, and today we will understand why the Q radiation is like that. Okay, but he basically said that the Q radiation is area times sigma times epsilon times T surface to power 4 minus T air to power 4. Sigma is given, epsilon is given, it's 0.2 for that aluminum. Okay, I guess because it's so bright, it's not radiating as much. If he was really black, he would be radiating like crazy. So if you want to reduce the radiation, you basically make the surface very bright or polished. He wouldn't radiate as much, right? So we have the sigma, we have the epsilon, we have the Ts, we have the T air, and the area, that's the area of a sphere, right? So it's 4 pi r square or pi d square, correct? Alright, so now all we need is the Q convection, right? And so for my Q convection, well, that's a sphere. Forced convection on a sphere. So this Q convection would be H A, right, multiplied by Ts minus T infinity, or Ts minus T air. And that H, how can I get my H? For convection over a sphere, I can't hear. Nusselt number, right? The H basically come from a Nusselt number. And the Nusselt number would be, we'll have the H D over K, and for a sphere this would be 2 plus 0.4 Reynolds based on diameter to power 1/2 plus 0.06 Reynolds D to power 2/3 Prandtl 0.4 mu infinity over mu s power 1/4, or any other equation for forced convection over a sphere, basically, right? And the property of those guys, because you need the Reynolds and you need the K and you need the mu infinity and the Prandtl, so you get all those property at T infinity, except for the mu s, which is basically evaluated at Ts. Alright? And so out of all this thing, you will get H equal to 205.6 watt per meter square Kelvin. And now you have Q convection and Q radiation. So it will turn out that dt by the time is by d squared, that's the area, over pi over 6 d cubed, that's the volume, rho CV, and over here you got Q convection and Q radiation, right? So Q convection is minus 2.88 10 to power 5, and that's per unit area, minus 0.95 10 to power 5 Q radiation. So you can see that the radiation actually cannot be neglected. It's actually more than the convection, right? And so you plug in all the number and you will get this as minus 1990 Kelvin per second. So every second he dropped almost 2,000. So basically in less than in less than 2 seconds he would be pretty cool. So actually start with 1700 Kelvin. So it will not take even a second for him to actually solidify. Alright? Question? Alright. So I have in the solution also another method for using another formula for forced convection over cylinder, over a sphere. And so, so another formula for the forced convection over a sphere will produce different H. So rather than H, this 2000, basically the H is actually rather than 200 watt per meter square in the second equation, it's 383. So then that makes the cooling even quicker because of the higher H. And this, rather than being 2000, almost 2000 Kelvin per second, it's actually 3000 Kelvin per second. Right? So I guess what I'm saying is that picking the formula for forced convection is very important, that you pick one that really match the temperature range you are working with. So some forced convection, I'm not just talking about sphere, but also about cylinders and plates, and so certain equations are valid for certain range. And if you take them out of their operating range where they have been tested and validated and force them to work in different range, they will produce different results. Probably wrong results. All right? Questions?